So the last question for the week number 3 is going to be about this example. Now, what do we have is a disk that we have, sorry, we're going to have a rod pinned to it at the point A. Now, we have the disk rolls without slipping such that it's going to has an angular acceleration alpha of 4 radian per second square, an angular velocity of omega equal to 2 radian per second at this instant shown. Now, definitely for this circle alone, we said there is no slipping. That means this point is going to be the IC for it. This point is going to be the IC. Now, determine the acceleration of the point A. We need to find the acceleration of the point A. That's the point A here. And also for the point B. On the link and the link angular acceleration at this instant. So we need to find also what will be the value for the omega during that. So of course, when this one is going to go to that direction, that means that this point is going to be pushed to the right. The velocity and the acceleration is going to be in that direction. And also the value for the alpha and the omega will be in that direction. At this point here, we're going to have two components for the acceleration. One of them is going to be in that direction, the other one is going to be on this direction. So what we need to find is the acceleration at the point A. Then I'm going to write down the relative velocity equation, acceleration for the link AB, and I'm going to be able to find the acceleration at the point B. So we start first with sketching the kinematic diagram, and it will tell me that this will be the acceleration A direction, and this will be the acceleration AC direction. We have known that the omega is equal to 2 radian per second, and the alpha is equal to 4 radian per second square. The unknowns are the acceleration A is unknown. It has two components, the AAX and the AAY, and we don't know what is the acceleration at the point B in meter per second square. And we are going to start first with the disk itself, and we know that the IC is going to be infinity, so that means simply the omega AB is going to be equal to 0. Okay, so the omega of the AB is equal to 0 because we have the IC is going to be at infinity. Now, we coming to the next step. The center of the acceleration, central acceleration is going to be equal to the AC is going to be equal to the omega square multiplied by the R value, which is 0.15. And again, to get the acceleration at the center is going to be equal to 0.6 meter per second square. Now the acceleration of the point A, we are going to write down the relative acceleration equation between this point and that point. So we are going to write down that the A at the point A is going to have two components, so we can write it down as a vector. It's going to be equal to the AC that we calculated, and this one is going to go only for the I value, plus the alpha multiplied by the R A to C, which is 0.15 J, and minus the omega square multiplied by the minus, sorry, not minus, 0.15 J. So now if I get to expand this one, I'm going to come to this equation, and you can see that we have 0.6 I here for the acceleration at A. The alpha is minus 4K multiplied by the RAC, which is 0.15 J, minus the omega square, which is 2 square, multiplied by 0.15 J. So by a simple solution for this one, we will come to the equation that the acceleration at the A is going to be 1.2 I minus 0.6 J meter per second square. Definitely I can find the acceleration at the point A if I'm going to find the magnitude of this acceleration, and it's going to be 1.34 meter per second square. And I can find the value for the theta if I want by doing the y over the x and find the tangent of this value, which is going to be equal to 26.6. So now we finish with the part A. Let's go to the part B, where we need to find the acceleration at the point B. So again, I'm going to write down the angular relative velocity, relative acceleration equation. Okay, and you can see that we already prepared this equation. Sorry, we have a typo here. Okay, so this is the AA, not the AB. So the AB is going to be equal to the AA plus the alpha AB multiplied by the RB slash A minus the omega AB square multiplied by the RB slash A. So that's the equation A we got from the previous step. This one is unknown as a components, and we are going to put the alpha AB, which is unknown, multiplied by the R A B. Now, to go from the A to B, I need to go to a positive value for the X. Okay, and this will be equal to 0.4 for that distance. And then I have to go to 0.3 meters to downward to the J. So it's going to be equal to negative because it's going to go downward. This was positive because it's going to the right. Now, the omega of the AB, as we mentioned earlier, is going to be equal to 0. So this whole part will go to 0. Then simply I'm going to assume, it's not assume, this one is only going to go horizontally. So this one also going to go to 0. Now by solving, I will have this one is I. The K multiplied by the J is minus I multiplied by minus is going to be positive, and everything else is going to be for the J. So we are going to solve for this equation, and then I'm going to divide it to the I's and the J's. And you can see that the unknowns we have here for this one, this is unknown, and that's unknown. For the second equation for the J, just the alpha is unknown, so I can solve for this equation, and I will get the value for the alpha AB, and I will substitute it in the first one, and I will get the value for the ABX. So that's the first one, and this will tell me that the alpha AB is going to be equal to 0.6 divided by 0.4, and this will make it 1.5 radian per second square. Now substitute in the first equation. Okay, you can see that I will have that the value for the ABX is equal to 1.2 plus 0.3 multiplied by 1.5. Okay, and this will give me that the ABX is equal to 1.65 meter per second square. So that's it for this question, and for any questions, just come back to me.